Here are more example problems about NMR. From this video, you should be able to identify chemically inequivalent proton environments and piece your NMR structures together. Near the end of the video, there will be some IR spectroscopy tips in identifying certain types of functional groups. In this example, we're given a molecule without the hydrogens drawn in. Their first step would be to draw in all the hydrogens so we know what we're working with. The next step is to identify how many chemically inequivalent hydrogens we have. In this molecule, there is symmetry. Where the line of symmetry is on the fourth carbon where the bromine is attached to. That means we only have to look at one side of the molecule, since the environment on the left side is the same as on the right side. Let's start with the very end of the molecule. The hydrogens on carbon A are in their own environment. There's a second methyl group attached, and also of the same chemical equivalency, since the bond rotates. So whether one is up or down does not matter, as both are connected to carbon B. Carbon C and carbon D are in their own environments, since they are connected differently than carbon A or B. Now that we have labeled the different types of hydrogens, we must talk about chemical shift. Electronegative atoms like nitrogen, oxygen, and halides withdraw electron density from surrounding atoms. This effect is what allows us to identify chemically inequivalent hydrogens. The closer the carbons with hydrogens attached to it are to the electronegative atom, the more downfield the proton NMR will read the chemical shift of the hydrogen's environment. We can also say the farther away a carbon is from the electronegative atom, the more upfield the hydrogen's chemical shift will be. So in simpler terms, downfield means bigger ppm value, while upfield means smaller ppm value. This is the part where you pull out your NMR chart table and familiarize yourself with it. For regular carbon-hydrogen attachments, the chemical shift will read from 1 to 2 ppm. Since a hydrogen environment is farther away from the bromine, it's closer to 1. The number of subpeaks is dependent on how many neighboring hydrogens are adjacent to the carbon you are looking at. For A, there's only a hydrogen attached at carbon B. Using n+1 rule, we see that the number of subpeaks will be 2, since 1 plus 1 is 2. The integration is where it gets tricky. We assume it's 6, since there are 2 carbons with the same equivalent hydrogen environments, but the molecule is symmetrical. For integration, you will need to double the number if the entire molecule is symmetrical, except for the point of symmetry, which happens to be the hydrogen environment at D. Remember, integration is the number of hydrogens quote-unquote living in that environment. The hydrogens at B are closer to the electronegative bromine, which will draw electron density, so the chemical shift will be more downfield at, let's say, around 1.5 ppm. The number of subpeaks is 9, since there are 8 neighboring hydrogens, 3 hydrogens from each A environment, and 2 hydrogen neighbors from the C environment. With the n+1 rule, we get 9. In a real NMR spectra, it would look a little messy and hard to tell, but subpeaks 6 and above are called multuplets. The integration of proton type B is 2, since there are 2 B environments in the entire molecule. At environment C, the integration is 4, since there are 2 hydrogens attached to that carbon, but the molecule is symmetrical, so we double the number. The chemical shift reads closer to 2 ppm, since the environment is closer to the bromine. The number of subpeaks using n+1 rule is 3, since we are looking at the adjacent hydrogens at carbon D and B. The carbon at the D environment has a bromine attached. If you look at your chart, you will see that it has a chemical shift of around 2.5 to 4.5 ppm, so we'll say 4 ppm. The number of subpeaks is 5, since there are 2 C-type hydrogen environments attached to it on each side. They both have 2 hydrogens each, so the number of neighbors is 4. Using n+1 rule, we get the number of subpeaks to be 5, which is a quintuplet. Since the line of symmetry is at the environment D, the integration is 1, since there's only 1 hydrogen living in this environment. From this table, you should be able to build the NMR of the molecule. Also, please ignore the integration of 2 for proton D, since that is a typo. It should be 1. Starting with proton type A, it is around 1 ppm and has an integration of 12, so it'll be very, very tall when compared to the other types. The number of subpeaks is 2, which is a doublet. For NMR, please make sure to place the tallest peak in the middle and decrease the size accordingly. Proton type B is around 1.5 ppm and a multuplet with 9 subpeaks, with an integration of 2. It should be relatively stubby when compared to proton type A, B, and C. Proton type C is around 2 ppm with 3 subpeaks and an integration of 4, so it should have the second tallest peak. Proton type D should be around 4 ppm with a quintuplet and an integration of 2. This should complete the NMR spectra of what you are expected to find when you run the machine. You can take an NMR spectra and build a molecule from it by making a table and piecing the hydrogen environments together. Given an example where an IR spectroscopy was run, and you see a broad, strong peak at the 3400 region, you think that maybe there may be an alcohol compound. Then you decide to run an NMR spectroscopy. Based on the NMR spectra, there are 3 hydrogen environments, which means there are 3 atoms with hydrogen attachments. Note that there may be atoms that don't have hydrogen attachments, which will not show up on the spectra. Integration is not always necessary to complete the structure of a compound, as you'll see on the ACS exam, which won't give them to you, so you'll solely have to rely on the n+1 sub-peak rule as well as the chemical shift value. For this example, I have included the integration, even though the spectra does not have it. For going from NMR spectra to compound, I like to start at the very end of the spectra. Remember, the 1 to 2 ppm region is usually saturated hydrogen environments, which just means alkane-type pieces. These environments are also more downfield due to the fact that they are farther away from electronegative groups. The second peak I'm going to label as environment B, and the third as environment C. I'm labeling the first peak as proton environment A. The first thing I'm going to note is the chemical shift, which is around 1.3 ppm. I usually take the chemical shift from the highest peak, or just around the middle. Next, I'm going to count the number of sub-peaks. Sometimes this can get a little messy, but do your best. Remember, 1 sub-peak is a singlet, 2 is a doublet, 3 is a triplet, 4 is quartet, 5 is quintet, anything 6 sub-peaks and above is a multuplet. Integration is given to you by the computer, so in this case it's 3. Proton environment B has an integration of 1, a splitting pattern of a singlet, and a chemical shift of 2.6 ppm. Proton environment C has a chemical shift of 3.7 ppm and a quintet for a splitting pattern, as well as an integration of 2. Now we can start piecing the molecule together. Some tips are that proton C is probably in the middle of the molecule since it has a quintet for a splitting pattern. Using n+1 rule, we see that it has 4 neighbors. Just because a proton environment is more downfield does not mean it's at the other end of the molecule. Some electronegative groups must be pulling it farther downfield, which suggests the proton environment B is actually next to the OH group. Proton environment A is at the very end of the molecule and probably farther away from the OH group, so it's likely at the very end of the molecule. You can tell since the integration is 3 and it's very downfield compared to everything else. The subpeak indicates it only has 2 neighbors, which suggests it's attached to a CH2 group. The integration of proton environment A just further confirms what we already know, that it's probably a CH3 group at the end of the molecule. Proton environment B is special. Since the proton environment C is so downfield, it must be next to the OH group, so it cannot be the OH proton environment. Looking at proton B's integration, we can see it's a singlet. This is very unique to OH protons when doing NMR. From the chart, you should be able to see that the NMR chemical shift value can be anywhere from 0.5 to 5 ppm. It's quite a large range, but there aren't many splitting patterns with the singlet, as well as the fact that the OH group made the proton environment C more downfield. From this, we can finally draw the molecule. Proton C's environment must be somewhere in the middle, with one of its neighbors being an OH group. Proton environment A must be the methyl group, while proton environment B is an alcohol functional group. The final molecule is ethanol. So benzene is a little weird, but you'll learn about it more in Orgo 2. So for now, just know that hydrogens and carbons within the environment are chemically equivalent or nearly chemically equivalent. Let's take toluene for example, and see how many different types of hydrogen environments there are. You'll notice a line of symmetry at the carbon where the methyl group is attached to. So if we label the methyl carbon as hydrogen environment A, the next 2 carbons must have the same chemical environment, and then the next 2 on that ring should have the same chemical environment. The carbon opposite to the carbon with the methyl group is where the line of symmetry is. It's a different proton environment since its connectivity is different. So there should be 4 different proton environments in toluene. In an NMR spectra, you'd see a multuplet at around 8.5 to 6.5 ppm. For carbon-13 NMR, integration is not a concern. Chemical shift is how you analyze and piece your molecule together. Carbons that do not have any hydrogens will show up on carbon-13 NMR. So the important takeaway is that when you see a splitting pattern of a quintet or above, it's most definitely in the middle or some point of attachment to two other atoms that have hydrogens. Know the range of the saturated hydrogens very well. They should stay within or near the 1 to 2 ppm range. Adjust the value based on how far away the electronegative groups are. If you see an integration of 3 with a triplet splitting pattern at 1 ppm or very near it, it's probably a methyl at the very end of the molecule. So now we'll move on to IR spectroscopy. IR cannot accomplish what NMR does. You cannot build the structure of a molecule with IR like you can with NMR. IR can only tell you the functional groups in the compound. What is in the spectra for IR is just as important as what isn't in the spectra. The easiest and most notable peak are the alcohol peaks, which are around the 3600 to 3200 region, and they're very broad. Carboxylic acids are around the 2500 region to the 3000 region, and look very similar to alcohol peaks, except for the fact that you can see some points sticking out from it, so it makes the whole peak look like a beard. The other way you've seen the carboxylic acid peak look like is a really jagged plateau. Both shapes are unique and identifiable to carboxylic acids. Carbonyl groups can get a little bit more confusing. An aldehyde and a ketone both have carbonyl groups, but only the aldehyde has a pair of peaks around the 2800 and 2700 region. So if you see a CO peak at around the 1700 region, look at the 2800 and 2700 region for 2 peaks. If it's not there, it's probably ketone. CH bond peaks for different hybridizations have a process when it comes to identifying which is which. Let's look at hexane, where all the CH bonds are sp3 hybridized. These CH sp3 hybridized peaks are below 3000. A good tip is to draw a line or use a piece of paper and line up the peak and see where it lies on the 3000 line. If it's under 3000, it's sp3. Next is hexene. It's got a pi bond, which means there are sp2 hybridized CH bonds. These peaks are above the 3000 region, but less than the 3100 region. So now we have 2 different types of CH bonds, which means 2 different types of CH peaks. Using the line method, we can see which one is which. Another good thing to look out for is the fact that there is a carbon-carbon double bond, which means there's a peak for it in the IR. This peak is usually sharp and of medium intensity. It's located around the 1640 to 1680 region. Lastly is hexine. It's got a triple bond, which means there are sp hybridized CH bonds. Those peaks are located at a higher wave number region than sp2 or sp3 hybridized CH peaks. There is also a peak for the carbon-carbon triple bond located at the 2100 region to 2260 region. Remember, in IR, it's important to see what peaks you have and don't have. If we take a look at hexane again, we can see it's quite empty. If you're given a range of compounds and have to match the IR, see what types of groups each compound has, and then see what kinds of peaks you have in each spectra. Another thing to keep in the back of your mind is conjugation, which are structures that have double, single, double bonds. Conjugation can shift peaks more to the right, sometimes out of the region where you would normally look for. Familiarize yourself with different types of IR and NMR spectra. OWL is a great resource for extra practice as well as a textbook.